Hey guys, Mr. Ferguson here on Wrestling with Math, and today we're going to actually create the equations for exponential growth and decay. Again, my general formula here for exponential growth and decay is listed, as well as the values here. Okay, my table is here, my x and y values 0, 1, 2, 3, and the y values that follow. Now we did do this previously. If you remember, if we did an exponential regression, EXP REG, with the graphing calculator, we plugged in L1 and L2, and it gave us the exponential function. We had to know that it was an exponential function. But how can we do this just given a table? So first off, are the numbers going up or down? Are they getting bigger or smaller in the y value? That's going to determine whether or not I'm using plus or minus. Okay, so if I look 0.1 to 0.05, 0.05 to 0.025, these numbers are getting smaller, which means that this is a decay or exponential decay. So since it's decay, I'm going to use the minus sign here. So if I were just to rewrite the formula here, 1 minus r to the n. Okay, now I'm just creating the formula here, so I'm going to keep that value as n, as t, whatever it may be. It could just be x if we're using the graphing calculator. P is my starting value. Well, if I'm looking at a table or of a graph, the starting value would be the y-intercept. The y-intercept on a table is where x is 0, which means this starting value is 0.1. So actually, they're going to have y equals. 0.1 is your p-value. I'm going to actually use x as my variable. 1 minus, how do we find the common ratio? Okay, well, just like we did with geometric sequence, I'm going to take one of these y values and divide it by the previous. So let's just go for this. I'm going to take 0.025, and I'm going to divide it by the previous term, or the previous y value. When I do this, I plug it into my calculator and I get 0.5, which means that this is, if I were to look at a percentage here, this is a 50% change here. Okay, so 0.5 is my decimal, that's my ratio. The good thing about this is it's not in percentage form, it's already in decimal form, so I'm going to plug it in as 0.5 there. Okay, here's my formula, which is awesome. Okay, so I could plug it in just like we see it here and I'd be done. You could, if you wanted to, simplify what's inside the parentheses. So I could have y equals, and y equals is already there, 0.1, 1 minus 0.5 is 0.5 to the x, and that could be your final answer. Either of these is acceptable. What this means is, since it was subtraction, this is, and 0.5 is my ratio here, this is a 50% decay if you did have to explain it. Okay, so here's one example again using the table. The starting value is the y-intercept where x is equal to 0. And just the same way we did a common ratio with sequences is how we would find that ratio or rate for exponential growth or decay. So hopefully this helped, and thanks a lot, guys.